from Caltech. Then he went to PSI, then CERN before coming to academic Sinica. He's an expert in experimental neutrino astrophysics and the dark matter search. And then the second one is second part of the talk is going to be given by Lin Shin-Ted. He's a got his PhD from National Taiwan University. Then he did a few years of postdocs in Henry's group. Now he's a professor at Sichuan University in China. Now let's welcome Henry.
Okay, so good afternoon. First of all, I'm also happens to be the deputy director of this institute. So on behalf of our institute, I also extend our warm welcome to all of you who come to this place to attend the nuclear physics school, and also thanks our colleague Taiwan to organize that. And we saw a lot of students around, and so which are very motivated. And then it is what the Institute of Physics, the Institute of Physics should be for. Yeah. So on this, I hope you enjoy the school, and also for those who come far away, enjoy Taipei, and will find occasions to come back again. So this is my official part. For the physics part, so I thank the organizers for giving us an opportunity to tell us what to share with you some of the things that we know. It started off as a more focused topic of what are the organizers would like to focus more on what are the aspects of some nuclear and atomic physics issues which is related to our work, experimental physics on dark matter and neutrinos. And we decided to expand it a little bit so that to include start off with a general survey of the dark matter problem for two reasons, because this is more of a general interest, and then not everyone are interested is directly relevant to cross sections in a particular nucleus called germanium. But the dark matter problem is, of course, one of the defining goal of this centuries in basic science. So we want to it's nice to share around, and also that this subject is also our group is also learning, and then master is trying to pick up here and there. We are by no means experts, so this is more a journal club styles to tell you what we know, and then maybe in the process try to induce some of you to think about the problem, and then we can have rooms to work together. So that defines how our motivations. So the first 35 to 40 minutes would be a general survey of the problem of dark matter, and along the way we'll come across a few points which may be related to we need to have this input from the nuclear physicists, and then I would emphasize that. And the second half would be a journal club style, seminar style from Dr. Lin, who has more expertise on select a few topics to give a flavor. What are the problems which experimentalists are facing? So now, starting from the basic, we only understand about 4% of the composition of the universe. So the standard model particles, which we love and learn pretty well. It's a marvelous achievement, but nevertheless, it's only around a few percent of the energy content of the universe. And by and large, we have 70% is dark energy, and then the rest is dark matter. Something which we give them a name, but then we don't really know. No, so we know nothing about dark matter, and then we know less than nothing about that energy. But on the focus of dark matter, which is for this talk, we don't know much, but then at least we may have some reasonable guesses. So we're starting from using our experience of building up the standard model, both theoretical and then experimental. We try to see what that experience may be helping us to attack the dark matter problems. So some of the experiments, as well as the formulation, the theory, you can trace the cultural root are from this sector. Whereas the dark energy may need a radically different approach. Okay, so before we learn what will happen to the next 100 years, so let's go wind the clock for 100 years. We learn from history. So 100 years ago, there's another missing energy problem, which is Chadwick measures the spectrum of the beta decay. Beta decay is an unstable nucleus emitting an electrons, and then at that time it was thought that there was a heavy nucleus emitting a light particle turning into another heavy nucleus. And in this case, the electron should be should be monoenergetic. But Chadwick and others find out that this is continuous and then with an endpoint with a structure like this. So this was 100 years ago, a dark energy, a missing energy problem. So it's not unlike the flavor nowadays. And the various ideas were postulated and then investigated, including evaluation of energy momentum conservation and so on. But eventually it took 20 years before a theorist, Pauli, would postulate the answer, which turns out eventually to be correct that it is not a two-body decay, but rather a three-body decay with the missing particle. It's missing because we cannot see it. We cannot see it because it doesn't interact strongly or interact electromagnetically, and it has to be light in order to give a spectrum like this. So already, by not seeing things, we already have some ideas about this new object, which subsequently Fermi would call it neutrinos. But it took another 26 years before experimentalists that worked at the reactor and designs ingenious experiment, Reines and Cohen, to actually prove that this hypothetical object, neutrino, from Pauli really exists. And 1956, and now it's 2014, it took half a century, 50 plus years, before we know that now, by now that we know that there are three flavors of neutrinos, they have masses, and then the three flavors have mixings. And also, but still, these are the things that we know, but the things that we still don't know about this neutrino, which we started the story 100 years ago, is that what is the mass spectrum? It is like the normal hierarchy or the inverter hierarchy, and we do not know the absolute mass scale, and we do not know whether the neutrino is a Dirac or Majorana particle. So it took, and the story still goes on. So one of the lessons to learn is that it is ingenious, and then we have to be patient to decipher the secrets of nature. Okay, evidence of dark matter. But we do know that we have problems, and then dark matter. We understand dark matter. We have observed dark matter only gravitationally. We never see have a totally convincing evidence that dark matter interact or the measures cross sections and so on. And the evidence for dark matter comes from by studying astronomers studying the sky and then studying the gravity of the sky, and finds that it is somewhat different from how we comprehend the universe in the accelerator in our control laboratory. So the snowball starts rolling down, and there are various observations on the galactic scale. Galactic scale is a small scale compared to the universe. In a cluster of galaxies scale and in the cosmological scale. So we encounter the missing energy density problem everywhere, from small scale to big scale, from the study of the spiral galaxies, clusters of galaxies, the structures, universe as a whole, and then also by studying the nuclear synthesis, which is the history of the universe. So both have the flavor of time and also the flavor of the content of the universe. No matter where we look, they are fundamental problems. They are fundamental missing energy problems, just like 100 years ago. We do not understand. And then I'll go through some of this and to give us a flavor. Well, in fact, the first persons to suggest that we may be having problems is Tsz-King, a Swiss astronomer in the States, who already 1930s has already by observing this clusters of galaxies, and then by observing the dynamics, suggests that there is the amount of substance that gives us light is only around 10% of the substance that gives us gravity. So this is already suggested almost 80 years ago. But it was until the 1970s when Rubin, this is an astronomer. I also like the contrast of these two pictures. So this is the flavor of this guy and the flavor of this guy. So this is the two extremes of a scientist. Sometimes you have to be very focused, and sometimes you have to be very wild in order to make progress. So and by now there are many cases of this, and wherever we look, in a single galactic scales, we can ask the questions as what is the velocity of matter as it goes from the center to the edge of the galaxy. If all the mass is associated with light, with substance that gives off light, then of course in this picture all the mass is here, and then as we get far away, it can be considered as a point source. And then Newton's law, Newton's inverse square law tells us that it would have a structure like this. But astronomers measures the rotational velocity of the stars and find out that this is a data, and we find it in many different spiral galaxies. And the explanations for that is, there's something that is beyond the mass that gives us light, would also give us gravity, and then that makes it keeps rising, keeps at least continually rising, and then so there's a substantial amount of a gravitational matter up in the form of halo far away from the core. So there's the missing energy density in the galactic scales. And on a clusters of galaxy scales, as from the gravitational lensing, there are various hierarchy of gravitational lensings, but the visually most stunning of those are pictures like this, in which massive objects can distort the space-times around and then can act as a lens, just like our lens in the focusing of light in our optics laboratory. And then because of the curvature of space-time, a point source behind this mass would appear as a ring. And indeed, astronomers see different rings at various parts of the galaxy. From the size of the ring and the various aspects, they can estimate how much gravitational mass that's distort our space-time there is. And by really looking at in this region of space where how much light there is, they can also estimate how much standard model particles that give us light there is. And again, gravitational mass is more than the luminous mass. Missing energy density problem at the clusters of galaxy scale, very different from the galaxy scale. So one galaxy is less than a point here. Yeah, and then we also observe the same problem as we study the evolution of the universe and the distribution of light and matter of the universe. So the universe, in a nutshell, in the simple-minded picture, starts off with a Big Bang, and there are initial density perturbations, and then within 1 minute, there's a big subject of nucleosynthesis, so which senses how the various nucleus are formed. So that is one of the achievement of science in the second half of the 20th century, and then there's certainly a lot of nuclear physics here. This is something observable. And by the time from time 0 to time of 300,000 years, the universe expands. It starts to cool down. It starts to cool down, and the temperature drops. The kinetic energy drops, and at some point, the elementary particles that live harmoniously here in equilibrium suddenly, at some point, breaks out of equilibrium. In particular, the proton and the electrons was used to be free, and then in good company with the gamma. But now they form hydrogen, and then the gamma further expansion, the gamma loses its energy, and then this cannot go reversely, and so hydrogen and photon gets decoupled. Matter and radiation get decoupled at 300,000 years. So now at this instant of time, we have matter, we have radiations, we have traces amount of heavy elements, and then the universe evolved. Then astronomers, 10 to the 10 years from that instance, tries to figure out how this matter would evolve to what we observe now, and how this radiation will evolve to what we observe now. So there are two distinct classes of astronomy to study the problem. One studies the distributions of matter in the universe, and one studies the fine details of the radiations in the form of cosmic microwave background in here. So these are, and then again, as we will see in the subsequent transparencies, they give the same conclusions that there is a lot of missing matters and energy density as in between. Okay, so that gives a flavor without getting into the details now. Now, the cosmic microwave background is one of the big achievements in astronomy and basic science in the last 20 years. Starting from COVID 20 years ago, the glass was like that. Good enough resolution to see important things, but then 10 more years the resolution is better, and 10 more years the resolution becomes even more exquisite. So this shows the progress of science in 1 decade. By observing the cosmic microwave background, these are the photons that got decoupled at time 300,000 years, and then by observing their temperature and then an isotropy in space, all the subtleties in a statistical way, astronomers can trace back how much matter are there in the universe. And the flavor of this idea is the following: that at the Big Bang, everything starts off as in a very small volume, but at the time of 300,000 years, the universe got substantially bigger. And then there's a length scale, which is a correlation scale. So the two difference points in space at that time is correlated from the same perturbations in the early universe, and that the correlation distance can be transformed into an angle when we observe it 10 to 10 years from now. And that angle depends on how light is propagated from these 2 points, from this point, and that defines the angle that we observe now. And so this angle will translate into how much substances, what is the mass density, energy density of the universe. So the first, when we observe this cosmic microwave background, the first minimum, the first maximum tells us how much, what is the total energy density of light that light has to go through from the decoupling time to us. And then subsequently, within this correlation length, it's not totally homogeneous. They are patches of the space that has a higher density and less density. And this is a competition between two facts. One is that the gravity tends to put mass together, but the radiation pressure tends to repel this attraction. And this depends on the gravitational mass. This depends on the barrier mass, the standard model mass. So although they deal with mass, but they are sensitive to two different mass terms in the mass processes, and therefore, subsequently by studying these ripples, tells us about how much baryons are there, how much standard model particles are there, and how much mass, how much gravitating mass are there in the universe. So by studying this, we learn about how much mass and how much baryons. Now we don't have to, and of course, if you are the professional astronomers and astronomy students who will spend 1 week just to learn how that is derived. This is radiation, and then the matter. The matter also evolved from early perturbations into the universe that observed today. And it turns out that if the matter, including the matter is made up mostly, the matter that gives us that is responding to our gravity are mostly from the dark matter sector. And it turns out that the dark matter has to be cold, that is non-relativistic, moving relatively slowly. In order the universe would evolve like the way that we observe now. By studying the structures of the distribution of matters in the universe, we can trace back that the dark matter has to be relatively slow, non-relativistic, in order to be agreeable. So here is one of the blue are observational data. The red is the simulation in the hot dark matter scenarios, and then you can differentiate them by eye. So they look similar. Whereas if dark matter would be light or relativistic, the universe would evolve in slightly rather different from what you observe. So from this we know that the dark matter exists as 25% of the mass energy density, and they have to be relatively slow, and at least non-relativistic. Besides matter, besides radiations, and then we have traces abundance of we have also heavy elements, helium, deuteron, and then helium-3. These are primordial. That means that they are these elements that we observe now are created from the early universe. And the astronomers can ask the question: how much helium-4 and so on are there in the universe? And then together with the nuclear physicists, they have to trace out how much matter you need in the universe to have a certain abundance. And it turns out that bing, 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 four different observations, measurements, independent, all point to the same amount of matter that is required to explain the data. So this is another spanned out over what? Tens of orders of magnitude, 10 minus 1, 10 to minus 10. Tens of magnitude, taking 4 measurements, they can explain by one number, which is the baryon content of the universe. And this baryon content is less than the mass content, including the dark matter mass. So we have confidence that the standard model, what we call the matter layout of the standard model, cannot be more than this amount, and this amount is less than what is required to explain the matter density of the universe. So we need something exotic beyond the standard model stuff to satisfy this inequality. Okay, so this is a very quick tour of what is the status now. But we try not to go into the details, but just have the most fundamental flavor of the science. So we have a crisis. We have also opportunities in basic science. So the total energy density of the universe is normalized to 1. It's more than the mass density. The mass is the one is those that obeys the laws of a special relative of a general relativity that gravitates, that lumps together. And this is more than the baryon density, the standard model particle. And again, not all standard model particle gives light. So this is a lot of Jupiter, and then a black hole and so on. So, but this inequality is the studies of astrophysicists. But this inequality, we give a name to try to explain it, but we call dark matter, but we don't really understand what it is, and we understand even less for this inequality that how come that we have more energy density than the mass that gives us the proper the classical gravity, and the rest of the energy density seems to be repelling. And then to express this inequality in the pie chart would be around 1/4 of the energy density is dark matter, 70% is dark energy, and around 5% is the thing that we know and love from the standard model part. And the various Nobel Prizes are related to it, obviously. Okay, now, and so before we go on to try to explain to try to invent solutions and so on, we also mentioned that there's a community of people, maybe an increasing community of people that tries to study the problem hard. Do we really understand gravity to the finest details? And they try to attack the problem not with inventing more particle, more energy, but tries to see what are the twists and turns that we can modify on the Einstein's theory, and tries to make progress on this. So progress has been modest in this area. Part of the reason is because this is a very complicated problem. That doesn't mean that it has to be a dead end, but so far that approach has some fundamental difficulties. And maybe if we work hard enough, we would crack the code with this approach. But so far, it has not been very successful. And to give a flavor, that one of the observational evidence that it is difficult to explain by modifying gravity alone is a picture like this. This is the bullet cluster. The bullet cluster is two high mass or two halos of galaxies. They collide. And when they collide, one can be, by studying the weak, there are some lensing effect, although it doesn't appear as a ring, but you can see that there are some weak lensing effect. That the astronomers can trace out the gravitational mass in green. But by observing the X-ray emissions, they can see the standard model mass, which is in red here. And you can see that there's two lumps of mass when they interact. Indeed, there are 4 centers of masses got separated. Both as here that do not interact, and this one that interacts in some amount. So pictures like this is a bullet cluster, and it's not easily explained by the present sophistication of the modified gravity theory. But I should mention that it doesn't mean that this approach has to be a dead end, and still a sizable community of people that tries to tackle problems, which is very reasonable, and we should stay tuned to that. So I have a cut through there. So now what I say just now is now turning into a simulation. Would be originally there are two well-behaved masses, the two well-behaved center of gravity, but when they come through each other, then it turns out that each lump of mass distribution has in fact can be separated into two different center of mass, depending on how much is it intact. So the red portions intact, and so they got slowed down. But the blue portion seems to ignore each other and then just goes through. Yeah. Okay. So this is one of the challenges that the gravity community has to confront. Okay. So now as in a very quick tour, in the 15 minutes, I just to by pinpointing the flavor of the physics, but not getting into the details, I try to give to share with you some of the primary physics flavor of the problem. Up to this transparency, things are pretty solid. The observation is highly elegant, highly robust. They are textbooks already. But so this established the problem. Similar, just like Chavik and so on has measured the beta spectrum. There's some missing energy that you can't. There's a big problem ahead, and then we can escape that. But from this point onwards, now where things may not be as clean because we are trying to guess a solution, and then my guess, somebody's guess is as good and as bad as the neighbor. So we should take this in mind. So the current wisdom is that. First of all, where are? I have to control this first. Where's the dark matter? So first of all, before we try to understand what it is, we try to find out where it is first. The where is that the conventional wisdom now is that this is our galaxies, and then we have a solar system is here. So the dark matter would exist as a halo around our galaxies, and then they would be slowly moving in non-relativistic speed. They're slowly moving so that they have, as an elementary particle, they have to be relatively heavy. So this is, and then but this is gravitationally bound. After all, it responds to gravity. And the velocity distributions at this point is most analysis assumes that it is an exponential distribution. So from our knowledge of statistical mechanics, but this again is still as we get on. This is some working hypothesis, but at the end we have to question everything that we put into this problem. And in order to be qualified for good solutions, people tend to have several criteria. So it has to be stable because there's a dark matter problem now. There was a dark matter problem in the early universe. So there should be some. In the particle physics language, some protected concept, quantum number, maybe some symmetry behind. No charge, no color, only weakly inacting. Therefore it is dark. It has to be cold, i.e. non-relativistic. That is the mass, is more than its kinetic energy. And so these are the general features. The positive features is that but we do know how much they have to be to add up to explain the problem. So the radic abundance is compatible observation. So this number is the 25% of the energy density of the universe. At least we have some numbers, observed number, 25%. So any explanation have to satisfy that number. And we also have other anomalies in particle physics and elsewhere. We want that maybe if we have invented solutions that can solve a few more problems, it would be more elegant and robust. But this is more a matter of taste. Okay, now, and then because from this criteria, so this is an incomplete list of a cold dark matter candidate. There's a lot. Of course, we will not go through all of them, and then it's not necessary to go through all of them. But there's a lessons to learn here. So now we are start trying to formulate the solution, and to formulate the solution, we have to choose our variable, and the variable of choice. The current wisdom is that the variable of choice